Hello everyone and welcome to the last day of applications of derivatives. As we know, we did the first day dealing with motion, the second day dealing with optimization, and now today's dealing with related rates. And this is a major concept in the idea of applications of derivatives. It's used quite a bit. So we know that a derivative is a slope, and we know the slope is a rate of change. And the slope being the rate of change is key when we look at related rates because we're looking at the derivative being the rate. So the first example we have here is air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. So make believe that we have a pump and it's actually going into the balloon at a constant rate, right? We're not actually blowing the balloon up. We're looking as the volume increases, the radius also increases, and if the volume is increasing at a steady rate, not necessarily the radius doesn't increase at a steady rate though, because as it gets bigger, the radius doesn't increase as quick. But we want to know here, and the key is how fast the radius is increasing when the diameter is 25. Well, we do know that when the diameter is 25, we also know the radius is 25. Sorry, when the diameter is 50, the radius is 25 centimeters. So that's the only question right there. It's two sentences. Air is being pumped into the spherical balloon, and the volume increases at a rate. This is derivative. So we're going to let V be volume of a sphere, and we're going to let R be the radius. That makes sense, right? And if we look here, the rate of change are the derivatives, as we said. And so if we look at dV dt, this is the rate at which the volume is changing with respect to time. That's equal to 100 centimeters cubed per second. Now, we're not going to worry about the units, but we'll write it down here. And dr dt, well, that's what we're looking for. How fast is the radius of the balloon increasing? So we're looking for dr dt when the radius is 25. So since we know that dr dt when the radius equals 25, this is what we're trying to find. Here's the key. You cannot plug in 25 until you have dr dt. So we're looking for this when the radius equals 25. And we have that there. I get that. But this is key. You cannot plug in 25 until we take the derivative. So if we look here, we have the volume of the sphere, 4/3 pi r cubed. We're going to take the derivative of that with respect to time. Again, the entire thing here is that the volume is increasing per second, right? So we got to take it all with respect to time. So the volume, take the volume with respect to time, and get dV over dt. Take r cubed, the derivative of that, since 4/3 pi is a constant. Bring the 3 down, it will cancel with that 3, so we're going to be left with 4 pi r squared dr dt. So now we have dr dt. This is what we're trying to find. Notice that we're trying to find dr dt when r equals 25. So when r equals 25, we can now plug in because that's what we're trying to find. So dv over dt equals 4 pi times 25 squared dr dt evaluated when r equals 25. Hey, that's good. That's what we've got. So now it's solving. Well, we know dv dt is 100 equals 4 pi times 25 squared dr dt when r equals 25. And if you take 4, I'm just going to do this here, 4 divided by 100 is 25. Divide that by 25 squared, we're going to be left with 1/25 pi equals dr dt when r equals 25. So our final answer is we're looking for how fast, you can't see that, how fast the radius of the balloon is increasing when the diameter is 50 centimeters. So the radius, and this is how we want to write it, the radius is increasing at a rate of 1/25 pi. Well, let's think of the units now. we got centimeters per second. So centimeters per second. And the radius is increasing, so there's no squared or anything there. Per second, done. Well, when the diameter is 50 centimeters. And that's how we would write it out. So just to recap, you write down the given. What were we given? We're given the volume. So we write down the volume equation. We have our givens. We know the volume is increasing at a rate of 100 centimeters squared per second, or cubed per second. We're trying to find dr dt when the radius is 25. Take the derivative. Hey, what is the practice calculus? So we take the derivative. We need to remember implicit differentiation. We're taking the derivative with respect to time, so we need dv dt and dr dt. We're trying to find dr dt when evaluated when r equals 25, so we plug in 25. We plugged in 100. We solved for dr dt. We got that, and we wrote it as a sentence. So hopefully, as you pause this and try to figure out what we just did, it starts to make a little more sense. So on to example 2, and if the first example didn't make sense, hopefully this will make more sense. Now pause it, read the question, try to draw your diagram. So we've got a ladder. The ladder is 10 feet long. Notice the ladder's length does not change here. It is 10 feet long. It does not change. If the bottom of the ladder slides away, notice here we're sliding away, that does. So the distance from the wall on the floor, the ladder is away from the bottom of the wall, does change. So we can't put a number to that yet. How fast is the top of the ladder sliding down? So we want to know the rate at which it's sliding down. That's a question mark. When the bottom of the ladder is 6 feet from the wall. So here we go. We have to put what we know. Well, what kind of shape did we just make? Well, we made a triangle, and so therefore if we have a right triangle specifically, we're going to use Pythagorean theorem. So we're going to label this A, B, C. And so we know that C is going to always equal 10 feet. That's a given. And we know that it's sliding away from the wall at 1 feet per second. So we know dB over dt equals 1 feet per second. Now notice that we're sliding away from the wall, and therefore it is positive. We know dA dt is what we're trying to find. But we're trying to find dA dt when the bottom of the ladder is 6 feet from the wall. So when we know B equals 6. That's what we're trying to find. So we've got a rate here. What is, and let's just go with this here, sorry for that movement. What is dC dt? Well, dC dt is the rate at which the ladder changes. The length of the ladder changes. Does the length of the ladder ever change? We already talked about that. The answer is no. So now it's 0. So what are we going to use? Well, we're going to use Pythagorean theorem because it's a right triangle. So we have a squared plus b squared equals c squared. And immediately it's calculus, so we know we take the derivative. So we're going to go 2a dA dt plus 2b dB dt equals 2c dC dt. And again, why do we have all of the rates of change? Because again, when we take the derivative of a with respect to t, we're going to be left with that dA dt. It's the rate at which that's changing with respect to time. So let's plug in what we know. Well, we know that we have 2a dA dt is what we're trying to find out. And b equals 6. Well, we can't put that in quote yet. No. Plus 2b times, well, we know that's 1, equals 2 times 10 times 0. So we're going to get 2a dA dt plus 2b equals 0. Well, that's nice, because now we only have 3 things that we're trying to find. Again, what are we doing? We're trying to find when this is 6. So over to the side, now that we have dA dt in the equation, we can find what it is when it's 6. Well, we have this triangle, and we want to know when this is 6, this is 10, what is a? Well, we can use Pythagorean theorem. 10 squared equals a squared plus 6 squared, and we know that's 100 equals a squared plus 36. And we know that's going to be 64 equals a squared, and so a equals 8. So now that we know a equals 8, we know the entire triangle. If we have an 8, 6, 10 triangle, or 4, 3, 5, 3, 4, 5 triangle, just double. This is what the triangle looks like when the bottom of the, if you look at the very last part, then the bottom of the ladder is 6 feet from the wall. Since we know what it looks like in immediately that point, and we have dt, we can plug in. So this is what we're going to get. 2 times a, 8, which is a, dt when b equals 6, plus 2 times 6 equals 0. All we did was plug in now that we had dt. So now it's just solving it. 16 dt when b equals 6 plus 12 equals 0. Subtract it over, you can get dA equals negative, well, 12 divided by 16, which is going to give us negative 3 over 4. And then we're looking for a rate, feet per second. So what does this tell us? It tells us that the rate at which A, and if we go back to the top, the rate at which A is falling, and we can't use falling because we have the negative there. I mean, we can say that, we just want to make sure the negative is taken away. So the rate at which A is falling when the ladder is 6 feet from the wall is 3/4 feet per second. So that's what it's decreasing at. And you're done. So we just write our statement now. The rate at which the ladder is falling is 3/4 feet per second when the ladder is 6 feet from the wall. And we're done. So again, the key is your givens right here. Get the formula you're going to use. Take the derivative. Find the derivative. When you get to where you can go no longer, use the given to be able to plug in all the other examples or all the other constants. Solve it, and you're going to get your rate of change. So on to the next example. I want you to pause it and draw it out and write all your givens like you have, which I have right now. So here's the tricky part of this problem. You're given a cone. You need to have drawn the cone. You are given everything here that you see right now. What can't we do? Well, you can't just plug in, because what we need to find is the height, is the radius when the height is 3. So one thing that we're going to do is use similar triangles. Do you agree if the water volume was here that we've just created similar triangles? And so that's what we need to look at. Whenever you're given the volume of a cone, we need to look at similar triangles. So we know the radius over height, you could do height over radius too, it's 2 over 4. We're going to cross multiply to get 4r equals 2h. And then you're going to choose which one to solve for based on, we need it in terms of h. So we need to get rid of the r. So we're going to do r equals 1/2 h. This is based off of similar triangles. We can't take the derivative of the volume of a cone with 3 different variables. And so based on what we are looking for, that h equals 3, I need to get this in terms of only h. I do that because these are similar triangles and create a proportion. And so therefore I can plug that in. So what I want you to do right now is plug in 1/2 h into there and solve for v, and simplify it. Take the derivative of v with respect to time, and then plug in and see what you get. Take a look at this answer. I wrote out all the steps. We will not be doing the last problem. I'll wait to do that in class. My corny joke is, why don't they play poker in the jungle? They have too many cheetahs. Ha ha ha. Oh boy. One thing before we do finish, make sure you notice how I wrote the last part here. I wrote out the sentence, which is important for any related race problem. And if you have any questions, come see me before class.